everyone, welcome back to lectures of aircraft structures. Today we are going to learn about torsion of non-circular shafts. So what we know from strength of material is T by J is equals to tau by R, which is equal to G theta by L. So let's consider a shaft which is circular in cross section and uniform along length. So this is the length L, and torque of T is applied to this circular shaft, and J is the polar moment of inertia, tau is the shear stress generated at distance r from the center, and G is the shear modulus, theta is the angle of twist, and L is the length of the shaft. So we know from strength of material that in circular cross section plane remains plane and no warping of cross section happen. Also we know in case of circular shaft that with respect to increment in the radius, that means say if it is the origin and if we move along the radius, the shear stress tau will increase and it will be maximum at the boundary point, which is the radius of the shaft. So this we know from strength of material. And in case of non-circular shafts with uniform cross section along the length, what happens is that there will be warping. So that means some points in the cross sections will go under deformation in z direction. So z direction displacement is W, which is warping, and this is present in non-circular shafts. Now this W is a function of x and y and independent of z. So location on z axis doesn't affect the value of W, but the position of that point in z plane, so if it is y and if it is x, then position of this point in this xy plane determines the displacement W in z direction. We can divide this torsion problem in non-circular shaft in different steps in order to derive the equation of warping and solution of warping function. So for example, getting the displacements from geometry and deformations. Second is strains from these deformations. Then stresses using constitutive equations and applying equilibrium equations to these stresses and force conditions. After getting these equilibrium equations, we will get one equation for the warping, and once you get that warping equation, we need to find the solution of that warping function. So in next step we'll see how stresses are acting on the boundary of the shaft. Say suppose if this is the z axis is coming out of the screen perpendicular to screen, and then this will be the tau zr, which is acting perpendicular to the boundary and also which is perpendicular to the z axis. Now r is the radial direction. So how shear stresses are acting on this boundary, then we'll see how the stresses are acting on this plane at the outer surface of the shaft. Once you get these, we'll solve equation obtained using equilibrium condition, or equilibrium equations. And for this we can use Prandtl stress function method. So let's start with first step, displacement. Consider a shaft subjected to torque T, and say this is the z direction, and this shaft is uniform, but cross section can be rectangular or elliptical or basically non-circular shaft. So let's say this is the cross section of shaft, this is the x direction, this is y direction, and z direction is coming out of plane from the screen. And if we apply torque T, this initial point P will move to next point P dash. Okay, and so this angle of twist is given by theta z, where theta is angle of twist per unit length, and if cross section is at distance z, then theta z will be the angle of twist. So I am redrawing this figure with enlarged view. So this is the point P. It moves to point P dash. So initial angle of P with respect to x is alpha. So what I am doing is I am drawing the components of deformation in x and y direction. So minus dx, because P is moving in negative x direction, and then dy is the positive. So this is the actual movement, and this angle is theta z, and if this length is r, then pp dash is equal to theta z into r. Now from the geometry we can see that if this angle is alpha, similarly this angle will be alpha, and then this angle will be alpha. So sin alpha, if p is x comma y, sin alpha is equals to y by r, and cos alpha is equals to x by r. So x direction displacement u is equals to, let's give one name here, q. So pq is equals to minus dx is equals to minus pp dash sin alpha, which is equals to minus theta z r y by r, which gives minus theta z y. V is equals to p dash q, which is equals to dy equals to pp dash cos alpha, which equals to theta z r x by r, which is equals to theta z x v. Then w, which is displacement in z direction, can be given as a function of xy. So we have now three displacement components. From these displacement components, strengths can be evaluated. So for example, normal strain in x direction, epsilon x, is given by dou u by dou x, which is equals to dou by dou x of minus theta z y, which is equals to 0. Similarly, sigma y equal epsilon y equal to epsilon z is equal to 0. All normal strains are 0. Coming to the shear strains, gamma xy can be given by dou u by dou y plus dou v by dou x, which is equals to, from this we can see, minus theta z plus theta z, which is equals to 0. Next shear strain is gamma xg, which is equal to dou u by dou z plus dou omega dou w by dou x, which is equals to minus theta y plus dou w dou x. Similarly, gamma yz is equals to dou v by dou z plus dou w by dou y, which is equals to theta x plus dou w by dou y. Now we can see that only two components which are in z plane are non-zero. So moving to next step, here we can establish the stress relations with strain. So we can evaluate stresses. All normal stresses are 0. Sigma x equal to 0 equal to sigma y equal to sigma z. Now gamma xy is 0, which implies that tau xy is also 0. So coming to tau xg, we can write it as g into minus theta y plus dou w by dou x, and tau yz is equal to g into theta x plus dou w by dou y. So these are two shear stresses which are non-zero acting on plane Z. Once you know these stresses, we can follow up the equilibrium equations. So next step is equilibrium equations. Sigma ij comma j plus fi is equals to 0 is the equilibrium set of equilibrium equations. So dou sigma x by dou x plus dou tau yx by dou y plus tau zx by tau z is equals to 0. This is 0, yx, this is 0. So zx is not a function of tau, zx is not a function of z. So that means this is also 0. So first equation satisfied. Next equation is sigma y dou y plus dou tau xy dou x plus dou tau zy dou z equal to 0. This is 0. Xy is 0 and zy is not function of z. So this term is 0. Again, this is also satisfied. Tau sigma z by dou z plus dou tau xg by dou x plus dou tau yz dou y is equals to 0. Now if we see, there are terms which are dependent on x and y. So this is 0, this is non-zero, this is non-zero. If we differentiate tau xg with respect to x and tau yz with respect to y and add them, we'll get g into dou square w dou x square plus dou square w by dou y square is equals to 0, which is equals to dou square w by dou x square plus dou square w by dou y square, which is equals to 0. So this is Laplace equation, and w is called warping function, which is the solution of Laplace equation. So till now we have derived the displacement, strains, and then stresses from those strains, and then we derived one equation, Laplace equation, from equilibrium equations, and we can see that this warping function is the solution of the Laplace equation. So in next class we'll see how this w warping function can be solved, and for that we'll see Prandtl stress function method. So see you in next class.